Speculative decoding is how we make large language models answer faster. A small helper model, the drafter, guesses several tokens ahead in parallel, and the big target model checks them in one pass. Every token the target accepts is free speedup. The longer the accepted run, the faster you go. So engineers train the drafter on a whole block of tokens at once, supervising every position against the correct answer. That sounds right. It is not. The verifier does not accept the whole block. It accepts a prefix up to the first mistake, then throws the rest away. So, a drafter trained on the full block spends most of its effort learning tokens that get discarded. Spec Auf is a one-line fix that trains the drafter on exactly the prefix the verifier keeps. Here is the mechanism. During training, let the drafter look at its own current guess for the block. Walk left to right. Find the first position where its greedy prediction disagrees with the correct token. Call that position J star, the breaker. Everything after J star never gets accepted at inference, so Spec Auf simply stops supervising there. The training loss applies only to the accepted prefix, plus that one breaker token. Improve the breaker and the accepted prefix grows. That is the whole idea. The mask is computed from the drafter's detached predictions, so it is not a gradient path, it is just a rule for where to focus the loss. No auxiliary objective, no verifier rollouts, no change to the inference pipeline, and no change to the exactness contract. Where does this sit among prior work? The paper shows that every block drafter training objective in the literature is one-weighted cross-entropy, differing only in the per-position credit they hand out. Methods like Griffin, focal loss, dpace, and specdiff all keep the full block and merely reweight it, handing softer or harder credit to each position. Spec Auf is the only one that truncates the support. It says, do not reweight the tokens the verifier throws away, just drop them. Even nicer, the paper proves this is the hard, argmax version of the soft acceptance gate that dpace uses. Replace each soft probability with its greedy indicator and the gate collapses to exactly the Spec Auf prefix. Minimal and principled. Truncating the support opens two knobs that fixed support objectives cannot move. First, the active token ratio, the fraction of the block actually in the loss. It starts small because the first error sits near the front, then grows rightward as the drafter improves. Second, the accuracy on just those active tokens. Spec Auf improves along both axes at once, an easy to hard curriculum the drafter sets for itself. And there is a bonus. Older recipes bolt on a hand-tuned exponential decay to weight earlier positions more. Once you truncate at the breaker, that decay does nothing measurable. Spec Auf removes a hyperparameter instead of adding one fewer knob to tune. Now the numbers. On Qwen3 8B with the D-Flash drafter, the average acceptance length climbs from 2.40 to 2.61. That is the headline, and it holds on every single one of the 6 benchmarks, math, code, and chat, under both greedy and sampling decode. More accepted tokens per verifier round means fewer rounds, means faster generation, at identical per iteration training cost. Spec Auf is a training recipe, not a new model. Same architecture, same compute, same forward pass. The drafter just learned where to pay attention. It also transfers. Domino is a different drafter, a 2-branch architecture with a proposer and a correction head. Apply Spec Auf to the proposer branch and its training loss drops sharply. The average acceptance length rises from 2.56 to 2.68, and every variant beats the decay-only baseline. Pushing Spec Auf onto the correction branch as well does not help and slightly hurts. A Freedom D-Flash's single distribution never exposes, so the gain is localized to the branch that actually proposes the tokens. 2 architecturally distinct drafters, same one-line loss fix, consistent lift. But here's the result that should mess with your intuition. On the fixed full block, the old decay-only baseline is the most token-accurate drafter of all. It gets more positions right, yet it is the slowest at decode, more accurate, but slower. That is the signature of the whole problem. Full block training optimizes a sum over positions, while inference rewards a product over the accepted prefix, and the two diverge exactly on the examples that decide speed. Spec Auf lifts that acceptance length, and you can literally see the accepted prefix stretch longer. A short accepted run becomes a long one. Honest scope. 4 caveats. First, one configuration only, block size 16, target Qwen3 8B, shared GPT training data. The claim that the rule is identical regardless of block size or backbone is a structural expectation, not a confirmation, because each would need a full retrain. Second, no head-to-head retraining against dpace under matched compute. Third, whether this stable supervised update is preferable to a tuned reinforcement learning objective or merely cheaper is untested. Fourth, the causal story, that aligning the loss with acceptance causes the speedup, is framed as a hypothesis needing interpretability work, not a proof. A clean recipe, not a closed case. Spec Auf is the Rebo's first training objective paper for drafters, where JetSpec attacks speculative decoding from the architecture side, and speculating experts from serving, Spec Auf attacks it from the loss side. 1 detached coefficient, 1 removed hyperparameter, gain on every benchmark. Subscribe for the next paper breakdown.